Aldol addition followed by dehydration. The purpose of this lab is to carry out an aldol condensation and dehydration between an unknown aldehyde and ketone and to identify the unknowns. Background. Aldol condensation has been long known as a method to form carbon-carbon bonds, and the base-promoted condensation between two different carbonyl compounds is no different. In this situation, the aldol product can dehydrate in order to form the alpha-beta unsaturated carbonyl. In the equation, the base-promoted addition of benzaldehyde and acetophenone with sodium hydroxide and ethanol or water forms this 1,3 product, then ending with the dehydration to form the trans 1,3 product. In techniques, recrystallization, solvent selection. There are two major points. First, the product is soluble at higher temperatures, but not at lower temperatures. And second, the potential impurities are soluble in the solvent at all temperatures. Techniques, microscale recrystallization. There are three major points. First is to use just enough hot solvent to dissolve all the desired solids. The second is to allow the solution to cool down slowly. And the third is to separate the solvent using a Hirsch funnel in vacuum filtration.
The equipment needed would be 1 ml graduated pipette, 25 ml Erlenmeyer flask, a magnetic stirrer, a test tube, and a Hirsch funnel. Procedure. Select a set of unknowns. The files contain enough of each compound for the aldol dehydration reaction and the preparation of a derivative. With a 1 ml graduated pipette, measure 0.8 ml of the unknown aldehyde and place it in a 25 ml Erlenmeyer flask. Using another 1 ml graduated pipette, measure 0.2 ml of the unknown ketone and add that compound to the same Erlenmeyer flask. Add 4 ml of 95% ethanol and 3 ml of 2 mol sodium hydroxide solution to the flask. Stir the solution with a magnetic stirrer for 15 minutes or longer. If precipitate is still forming, if the solution is only cloudy or very little precipitate has formed after 15 minutes, heat the reaction mixture in a water bath for 10 to 15 minutes. Cool to room temperature. When precipitation is complete, cool the flask in an ice water bath for 10 minutes. While the flask is cooling, place 8 ml of 95% ethanol in a test tube. Repeat this procedure with 4 ml of 4% acetic acid in 95% ethanol. Chill the test tubes containing these solutions in the ice water bath. Collect the product by vacuum filtration on a Buchner funnel or Hirsch funnel. Disconnect the vacuum and rinse the product with 4 ml of the ice-cold ethanol. Reconnect the vacuum and draw the liquid from the product. Repeat this washing procedure with the 4 ml of ethanol solution or acetic acid, and finally wash the crude product with the remaining 4 ml of ethanol. Before recrystallizing the crude product, you need to find a suitable solvent. Test 95% ethanol and toluene. The addition of a few drops of hexane may be necessary to promote crystallization from a toluene solution. If neither of these recrystallization solvents is satisfactory for your aldol dehydration product, test a 9-to-1 mixture of 95% ethanol or acetone. Once you have selected a suitable solvent, carry out the recrystallization. Allow the recrystallized product to dry until the next laboratory period. Weigh your aldol dehydration product and determine its melting point. Obtain an NMR/IR in melting point of your product. For data and calculations, acetone we used is 0.2 ml, benzaldehyde is 0.8 ml, and the crude product is 0.295 grams. And the recrystallized product is 0.143 grams. The melting point would be 103.5 degrees Celsius to 105 degrees Celsius. Due to 2-to-1 reaction, 0.632 gram of product is expected, and the percent yield is 22.59%.
The IR spectra showed 4 important peaks. The first peak, with a frequency of about 3052 to 3026, indicated a sp2 hybridized CH stretch of weak strength and sharp shape. The second peak, at around 1648 frequency, indicated a carbonyl ketone functional group stretch of strong strength and sharp shape. The third peak, at around 1625 frequency, indicated a double bond alkene stretch of weak strength and sharp shape. The fourth peak, at around 1589 to 1447 in frequency, indicated a carbon-carbon aromatic ring of weak strength and sharp shape. The results showed that an aldehyde functional group disappeared and a ketone appeared. The sp2 hybridized CH and alkene functional groups found on the IR spectra demonstrate that the desired product was obtained. The carbon NMR shows 6 unique carbons. Carbon A shows a chemical shift of 179.6 ppm. Carbon B has a chemical shift of 143.6 ppm. Carbon C has a chemical shift of 134.7 ppm. Carbon D has a chemical shift of 128.7 ppm. Carbon E has a chemical shift of 127.3 ppm. And finally, carbon F has a chemical shift of 117.8 ppm. There are 4 significant peaks in the HMR of this product. A has a chemical shift of 7.62 ppm and an integration of 2.01, which shows the symmetrical protons on the benzene ring are closer to the carbonyl group, and this is more downfield. B has a chemical shift of 7.42 ppm and an integration of 3.41, which proves the 3 symmetrical protons in the benzene ring are furthest from the carbonyl group and are slightly upfield to A. D is the gamma proton of the carbonyl group, which has a chemical shift of 7.75 ppm and an integration of 1. This is the most downfield. Lastly, C is the most upfield and has a chemical shift of 6.9 ppm with an integration of 1. This is the beta proton near the carbonyl group. The reason for the deshielding effect is that the gamma carbon deshields the gamma proton because of resonance. The product is a trans isomer because of wide doublets in the NMR, and this results in a larger coupling constant. Because both of the doublets have the same width in regards to splitting, the 2 alkene groups are thought to be trans. Here we have the Cauchy spectra, which shows a peak at 6.7 ppm and a peak at 7.5 ppm. These peaks are cross peaks that signify neighboring protons. And lastly, we have our bibliography. Thank you.